Hi folks, this is Dr. Mughal here again. Uh, Today is a very interesting tutorial in which I'm actually going to design a 4-bit adder, which will basically comprise of four full 1-bit adder circuit with an overflow detector. We also sometimes refer it to as 2's complement adder. So if you look at this block diagram right here, what's going to happen, we're going to have 4-bit numbers A0, A1, A2, and A3. We're going to add it to a 4-bit number B0, B1, B2, and B3. These individual bits will go through 4 full adders because we got 4 bits. And then if there's a carry out, it will go to the next block, next full adder, and then similarly it goes on and on. The answer for the 1 full bit adder is gonna be displayed over here. Our goal is actually to take these numbers at the bottom, which displays the binary output of these two 4-bit numbers, and then display it on a 7 segment. In addition, what we want to do here is also we would want this design to tell us whether the 4-bit numbers that we are adding, will that give us an overflow or not. Okay, so the first thing that we need to do is we need to come up with an expression for a 7 segment, which will take S3, S2, S1, and S0 as inputs, and then display it on a 7 segment in decimal. The second thing that we're going to do here is actually going to come up with 1 full bit adder, and then we are going to create 4 more by extensiating that full adders, in last we are going to put the system together in our top module and see if we can get it to work. So let's begin. So moving on to our task 1, which is going to be designing basically a 7 segment. So in order to do that, we have to drive an expression for a 7 segment using the logism. So I'm actually going to leave a link on the screen where you can go and watch the tutorial on how to do that. But here are the expressions for the segments A and all the way to G. I'm going to just copy these segments and paste it into the Vivado. 7 segments and then SEG. Okay. All right. With this, I am actually done with my code for the 7 segment part. Let's save it and synthesize it. Also making sure, oh, there are 2 critical errors. Let's see, what are they? Input. Okay, all right, that needs to be output. Output, because we are assigning value to it, so that needs to be output. Save it again, and then there are 2 more errors. Okay, it looks like I was missing a comma here. And now that I have that comma, let's save it again. And there are 2 critical errors at the end module. I got 2 of those. There should be only 1. Let's save it again. This time, looks like it went through without any errors. I'm going to click on the source file, which is 7 segment, and then run synthesis. Make sure I don't have any errors. Just to make sure. It takes a few seconds, so just be patient. All right, yay! So it was synthesized successfully, and it went through. So move on to our task 2, which would be designing a 1 full bit adder. So I'm gonna right click here, add source, click next, create a file. This is going to be 1 full bit 1 bit full adder. Here, click OK, click finish. Now remember, I'm going to take you over here. So we are actually getting a logic expression for a 1-bit full adder. So we have 3 inputs, A, B, carry in, and then 2 outputs, C out and sum. Again, using the logism, completing the truth table for these inputs and set of these inputs and outputs, we get this equation for C out and sum right here. Again, I'm going to copy these equations right here and paste it into a Verilog file. But let's just finish this source file first. So we got two inputs, A and B, and then we also have a carry in, and then sum as one of the outputs, and then C out as one of the outputs. So let's assign them as outputs, click OK, and here is your file right here. Okay, only thing I need to do is assign value to sum. So right here, assign sum equals to here and paste over here. Make sure I have these operators in between. The plus sign is replaced by a vertical sign. And then similarly doing it for C out. Here and then paste it in. Right here. All right, our code is complete. I'm going to save it. Yeah, and let's and let's synthesize. Well, there are two warnings right here. Yes, there are. Syntax error near CN. Okay, okay, yeah, I'm missing a AND operator here. Okay, all right, sweet. This looks fine. Save it again. Right, this time looks like it went through. I'm going to select the source file and synthesize it again. So again, this was successful. Remember guys, you don't really have to do it every time for every source file. I just like to do it because I want to make sure each source file is properly synthesized and there's no error. Now moving on to task 3. And that task 3 is basically driving the logic expression for 2's complement addition with overflow detection. So remember, I showed you one block diagram over here, right here. We have created one of these blocks for full adder. Okay, we have to have 4 of those in order to perform addition on 2 4 full bit numbers. So we're going to do that by basically extensiating these the single 1 bit full adder that we created. Okay, so looking at the inputs right here, those inputs are going to be A0, B0, C1, A1, B1, A2, B2, A3, B3, and then all these carriers, CN, C1, C2, C3, and C out. The outputs are going to be S0, S1, S2, and S3. I might use different variables, but I'm just trying to explain you using this block diagram what are your inputs and outputs are going to be. In addition to these these individual bits which will be your outputs, you will also need one more output that would detect whether there's an overflow when the addition was performed. So these could be unsigned numbers or signed numbers. In case of the signed numbers, for detecting the overflow, the equation is pretty much going to be the same what we had for the C out. So anytime when you're adding 2 bits and there is a carry out, that means there's an overflow. Well, when you are adding 2 signed numbers, meaning they have a negative sign, there are some rules. Adding 2 opposite sign operands, there will be no overflow. If you look at the A's and B's right here, 0 and 1, these are opposite, right? 0 being positive, 1 being negative, there can never be overflow. Again, adding 0, 1, there is not going to be an overflow. Overflow happens when 2 operands are positive and sum is negative. When you are adding 2 positive numbers right, like the case over here, two positive numbers, and the sum is negative. That means there is going to be an overflow. That's what you see over here. And similarly, when you are adding two negative numbers and the sum is 0, so you are going to have an overflow. Okay, we use K-map right here to get the equation for the overflow in case of the signed numbers. And it came out to be a bar, b bar, cn plus a, b, cn bar. With respect to cn and c out, you can also come up with an equation, and that would be carry in exclusive o-ring with c out. And that's what we have used here, cn, which is basically c3 over here, exclusive o-ring with c out. Okay, now so I'm going to copy these equations and paste it into our Vivado and get the task 3 done. And for that, I'm going to right click here again and create a new source file. And then I'm going to create a file, and I'm gonna name this one 4-bit header. Click OK, click finish. Okay, so putting our inputs here again, I'm just gonna switch back over here. So we got A0, A1, A2, and A3. So A, and then input as a bus, and this will then we have B here, and then B0 goes to B3, so again it's a bus. Okay. The outputs right here, so those are basically sum, S0, S1, S2, and S3. So I'm just gonna say sum here, and again this is a bus, so this will be 3. Okay, all right. We also need overflow, and we need 2 overflows. This one is only for the negative numbers. So for the negative numbers, I'm gonna say overflow signed. This is the negative numbers, and overflow for the unsigned numbers. And that is pretty much it. And these are going to be the outputs right here. We're going to connect these two with the LEDs, but some, if we like, we can add it to our LEDs also, but we're gonna connect it to the 7th segment. That's why we created. So we are almost getting the task 3 done. I'm just gonna click OK. It's gonna create a skeleton code for me. So I'm gonna click at the 4-bit header. Yeah, over here. Now, so looking at this functional block diagram again, notice we just created one of the blocks which we named as 1-bit full header. Now we are going to instantiate that block, that module, 4 times in order to make it 4-bit header. So let's get the coding going for that. We have already declared our inputs and outputs. Let's just declare wires as well. Remember, you wire something that connects the output of one to the input of another. So we need wires for C out 1, C out 2, C out 3, and 4. I'm gonna name it as 0, 1, 2, and 3. So let's go back to Vivado here. So declaring our C out as an array, we need 4 of those. So this is our C out. Okay, we are going to call that module that we created, which was 1-bit full header, followed by a blank space, and then the identifier, which could be anything. I'm gonna say U0, and then let's look at the inputs to the first functional block right here. The inputs are A0, B0, this carry in being 0, and then C out. Okay, all right. So we're gonna have A0, B0, and then 0 carry in as an inputs, and then we have sum 0 as an output, and then we have C out. Also, let's close the parenthesis, followed by a semicolon sign. Remember what we are doing here. We are basically instantiating the 1-bit full header 4 times create a 4-bit header. Okay, I'm just gonna copy and make sure this exactly matches with the module name or the source file that you created earlier. So I'm just gonna copy and paste it right here 4 times. Right. Notice here that this functional block right here, the inputs are A1, B1, output is S1, and then you also have this carry out right here, and this carry in right here. So this is C out 0, this is C out 1, A1, B1, and your sum S1 as in your output. So this will be A1, B1, and then C out 0 as your inputs, sum 1 as an output, and C out 1 here. Similarly, this will be 2, this will be 3, this will be 2, this will be 3. Just copy this thing and paste it over here. And then 2 here, 3 here, and then this will be C out 3 here, this will be 2 here. Okay, so if you look at the last one, this right here, this block right here, A and 3 being inputs, and then the carry out 2 also going into the block, and then sum 3 and C out 3 being output, which is actually this block right here, A3, B3 in, and S3 as an output right here. You have this carry in going in here, which is the carry out coming from this block, and then we have this C out, which we have labeled as C out 3. Okay. We also have the output, the 2 other outputs, which is the overflow for the signed bit and overflow for the unsigned bit. So we're going to use the assign statement, OB underscore unsigned. So again, I'll go back here. So if you notice, if you are adding 2 4-bit numbers, you got adding 2 4-bit numbers. So if it generates an extra bit, that means it is going to be a 5-bit now instead of 4, and therefore you would think there is an overflow here, correct? So what is that extra bit that is generated over here? That extra bit is the C out, right, which we have labeled in this as C out 3. Okay, we always look at the most significant bits. Okay, so the most significant bit over here is 1 and 0. When you add them, it creates a carry out, which could be 0 and 1 depending upon what you're doing, and this is in case of the unsigned numbers. So this part is done. We're gonna do the same thing for the overflow for the signed number, meaning one of the or both of the numbers are negative. Okay, in that case we implemented this rule right here and came up with a truth table, used the K-map to come up with an expression for the overflow, and it came out to be C in exclusive ORing with C out. Again, we look at the most significant bit, or this block right here. C in is this thing right here, and C out is this thing right here, which we have labeled as C out 2 and C out 3. So in other words, we can say C out 2 exclusive ORing with C out 3, and that sums up our code. Let's go ahead and save it, and we also have to make sure that we have a unique identifier for each of these modules here. So I'm going to change it to U1, U2, and U3, making sure all my semicolon signs are here, and then save it and then run synthesis. All right, perfect, awesome. So it was synthesized successfully, and then we're gonna move on to our next step now. Just task number 4, creating a top module. I just want you to look at the same block diagram again. It's the same block diagram. There's nothing change in it is just I have changed the orientation. So these are the inputs A0, B0, and those are represented by the switches that we are going to use. You see that initially the carry in going in is 0 obviously, and then C1 wires, which is then all blue that you see are wires that we had declared, and then we have this overflow as well. Okay, and this is for the sign. For the unsigned, there's another overflow that we created in the previous file, which you don't see it over here. And then you have this S0, S1, S2, and S3, which is basically be then connected to your your 7-segment display. So looking at the larger picture, looking at the top module, our inputs are going to be A and B, and we have 4 of those, so we're going to create an array. The output is going to be some 0, some 1, some 2, some 3. Basically you get 4 bits, and then you have the overflow for the signed and overflow for the unsigned. We also have wires, which are basically carry-ins and carry out. Okay, all right, so another source file here, click next, create file, and I'll just say top module. Okay, click OK, finish. Here the A0, A1, A2, A3, B0, B1, B2, B3. Okay. You have the enable for the 7 segments. Those are outputs. Okay. You got 4 segments of 4 enables. You got segments. These will be outputs also. Okay. Those will be registered as outputs. Click OK. So here is our top module. I'm just going to add 2 more things here. Remember, we got output for overflow signed, comma, and then output overflow underscore unsigned. Okay. All right. In order to finish the code, we're gonna have to add the 2 modules. So instantiating the 4-bit header and 7 segment modules here. So I'm gonna have to make sure that the name of the module exactly matches with the one that I have over here. So it's got 4-bit header, say this 5, and then A, the inputs B, and then some is an output, and also overflow for the signed bit and the overflow unsigned bit as the outputs, and then the 7 segment module, which is right here. Again, I have to make sure it matches with the name of the module. The sum, which are the lines that go into the 7 segment, the segment itself, and then the enable to enable the 4 LCD segments. And with this, I'm actually going to my code over here, and I'm gonna save it. Just to expedite the process, I also went ahead and edited the constraint file, and here are all my constraints. Remember, we got 8 switches, so those switches are right here. Make sure these input variable names matches exactly with the one that you have in your code. I got 2 LEDs, one for the overflow for the signed bit and one for the overflow for the unsigned. I got the 7 segment displays. I got you're gonna have to experiment a little whether to start with seg 0 and then start increasing and go all the way to 6, or start with seg 6. So it worked out for me like this, and these are the 4 enables for enabling the 4 LCDs. I think I'm pretty much done now. I'm going to save everything, choose my top module, and click on implementation here. And because my synthesis is out of date, so it's gonna run the synthesis first and then followed by the implementation. So it may take a minute or so, so let's watch out for it. Implementation is complete. It took roughly a minute and a half, maybe close to 2 minutes. Now we're going to generate the bit stream, so let's click here, and then again it may take a few seconds. You'll see the status on the top right corner of the screen. Once the bit stream file is created, it will open this dialog box and you put a check on Open Hardware Manager. You then go here, click on Open Target, choose Open New Target, click Next here. Make sure you have this local server selected, and then choose your device and click Next here. Click Finish. Once you are done with that, you choose Program Device. When you click on it, you'll see this small rectangle right here dialog box with your processor, your chip on it. Select this thing. It will automatically upload your bit file that it had created earlier. You click Program, and once the program is written, you should be able to implement your logic design has been implemented. And let's now look at how the Basys 3 board looks like now. So here is our Basys 3 board. You see the switches at the bottom right here. So this is my A0 right here, A1, A2, and A3, and this is my B0, B1, B2, and B3. And as I would change the logic over here, so I'm basically selecting 1 here. So you see 1 on the screen on the LED 7 segment. Notice we got 1 displayed on all 4 segments because we have enabled all 4 of them. There's a way we can only enable 1 of them, or we can have different numbers on those different 7 segments, but that's not the part of this lab right here. So say if you want to add 8 plus 1, so we got 1 already set. I need to change this switch right here to 1. Okay, so I have 1 0 0 0, that makes 8, and then 0 0 0 1, that makes 1. 8 plus 1 is 9, and that's what you see over here. Also, say if I have the first number, which is 8, so 1 0 0 0 makes an 8, and then I have 7. So 8 plus 7 makes 15, which is the F, and that's what you see. Okay, if I make it 7 plus 9, that makes 16, and because 16 is a 5-bit code, it's give us an overflow, and that's the LED lights up. Okay, so this is your 4-bit 2s complement adder. So right now I have you so you have the first 4 bits set to 1, and then the next set of 4 bits is also set to 1, so you got 1 plus 1, and it is displaying 2. So you have learned how to create a 4-bit adder with the 2's complement with the overflow detector. This sums up our presentation, and I'll see you guys in another video. Thank you for watching. Bye.